Hi, and welcome to another lesson in the physics video series. Today we're going to look at tension in the hanging mass, which is a statics problem. We're going to take a look at the resolution of vectors and how they keep this box hanging by two cables. Okay, let's get started. Clearly, we can see that we have two wires holding up this box off the ceiling, and each wire is at an equal angle. There is a more complicated problem where the angles are different, but we're going to start with this simple problem. When we look inside the vector breakdown, the resolution of the tension in each cable, we're going to see that the wire, which is on a diagonal, gives us the direction of pulling force through the cable on the box. This is in fact called tension. If I was to come with a scissor and cut anywhere along this wire, the box would swing away. So therefore tension is pointing up the wire. If I was to come along and cut this wire with a scissor, then the box would swing away in this direction, the downward direction. So therefore tension is pointing up in this wire. Tension is the stretching pulling force inside of a wire. It is being resisted by the weight of this block, mg. The black arrow pointing down represents the vector of the weight. When we look at this pair of vectors of tension, we see that T1 is clearly a first quadrant vector and T2 is clearly a second quadrant vector. Let's take a look at the resolution. Vector T1 can be resolved into a horizontal and vertical component by analyzing only its x rightward pull and its y upward pull. Tx is part of the vector that pulls to the right, and Ty is the component that pulls up. T2 vector as well can be resolved into its horizontal and vertical component. The T2x pulls to the left while the T2y lifts. Let's take a look at the trigonometry for the vector resolution. T1x is adjacent to the angle theta. So T1x will be equal to the full tension times the cosine of this angle. And T1y is opposite. So therefore it will equal T1 sine theta. Similarly, T2x is adjacent to this angle on the left side, and it is T2 cosine theta. And T2y is opposite and will be T2 sine theta. Now that we have expressions for the vector components of both tensions, we now have green only on the horizontals and blue only on the vertical. Let's take a look at the static equations. Here we have the net force equation for the x-axis and the y-axis respectively. Let's take a look at the x-axis first. We know that the net force has to equal to ma. The net force in the case of a horizontal group of vectors is right minus left equals ma on the x. That's what that little subscript x means. But since there is no side-to-side movement, there is no acceleration. And so this a term cancels to 0, leaving us with T1x minus T2x equals 0. Or, very simply, T1x equals T2x. And of course, when we write out the full trigonometric form, we get T1 cosine theta equals T2 cosine theta. Canceling cosines leaves us with what we already expected, that the tension in both cables is the same. T1 equals T2. So that's a very important conclusion. Let's just take a look at the diagram. What we're seeing is the green T1x being equal and opposite to the green T2x. Since the object is not accelerating to the right or to the left, the T1x and the T2x are a type of tug of war. No one is winning. These two are equal and opposite. Now we're going to focus our attention to everything that's on the vertical component, and that's the blue vectors T1y and T2y and the weight vector. You should be able to see that the two blue vectors T1y and T2y should be adding up to be equal and opposite to the downward vector. Let's take a look at the math and prove that. So here we are at the F-net equation for the vertical components. The sum of the forces on the y-axis is equal to the mass of the object times acceleration on the y-axis. But, as we have already discussed, there is no acceleration on the y-axis. A equals 0, making the right side of this equal to 0. And of course, the sum of all forces on the y-axis, all the forces pointing up minus all the forces pointing down. T1y and T2y are both pointing up, and therefore they're positive. T1y plus T2y minus the weight equals 0. So now we've proven in just this step alone that the weight is being perfectly balanced by the two vertical component forces of T1y and T2y. When we expand this trigonometry, T1 sine theta plus T2 sine theta equals mg, T1 sine theta and T2 sine theta. But what did we learn just a moment ago in the x equation? That T1 and T2 are equal. If they're both equal, we can just call it capital letter T and drop the subscript, and so we have T sine theta plus T sine theta equals mass gravity. You add this, you get 2T sine theta equals mass times gravity. Solving for tension gives you T equals the weight of the object divided by 2 sine theta. This conclusion computes the tension in both cables. Let's just take a look one more time at the picture. And here we are at the picture. And as I mentioned before, the T1x, the T2x, which are green, have canceled each other out, so they're equal and opposite. And in a similar way, the blue vectors T1y and T2y, they add up and cancel against the downward vector. There is no acceleration in the vertical direction. So these two blue vectors have to add up to be equal and opposite to the weight. And it should make sense to you, especially when the angles are equal, that both of these blue vectors are really half the weight. If this has a mass of 10 kilograms, this is 100 newtons. That means both blue vectors would be 50 newtons each. 50 plus 50 is 100 pointing up, canceling 100 pointing down. So in context, we can see that tension in the hanging mass is an easily solved problem, especially when the angles are equal. The two horizontal components cancel each other out to prevent any sideways movement, and the two blue vertical components add together to balance out the weight. They pull up or hold up the weight that wants to fall down. Let's now do a quick examination of the magnitudes of tension based on this formula, T equals mg over 2 sine theta, for varying angles from 90 degrees down to 0 degrees. Let's let the weight of this object, mg, equal 10 newtons. It's an easy number to work with. And let's say that we held this box with two cables pointing straight up that make 90 degrees to the surface. Mg over 2 sine 90. Sine 90 is 1, so that's mg over 2. 10 newtons over 2 is 5 newtons each. So when the box is being held with two cables, each cable has exactly half the weight of the box. It's going to turn out that every vertical component is going to have half the weight. However, the tension total is going to be this orange line. Let's take a look when we switch the angle and we make it 75 degrees. So we still have a steep angle. We're not at 90 degrees anymore, but we're at 75. So mg over 2 sine theta, 10 over 2 sine 75, gives us 5.17 newtons. So it takes a little extra tension when you're not perfectly straight to hold up the block, because you are now beginning to shrink the vertical component slightly. So you have to pull a little harder along the angle of tension. Let's reduce the angle to 60 degrees. Here we can see when the angle is 60 degrees, T is mg over 2 sine 60 equals 5.77. So we have to pull even harder along the orange vector because the lower angle reduces the amount of blue vertical force. But it has to be equal and opposite to the weight in order to hold it up. Let's take a look at 45 degrees. In 45 degrees, mg over 2 sine theta, 2 sine 45, you get 7.07 newtons. So you have to pull with 7 newtons off of the diagonal to hold up something that weighs 10 newtons total, because the blue vertical component is 5 newtons to match the other vertical component. So 5 plus 5 will always equal 10. But the problem is, as you lower the angle, you elongate the x component and you are shortening the y component, so you have to have a higher magnitude tension to accommodate so you have enough vertical component to still hold up your box. Let's go to 30 degrees. Here we have a very interesting situation. At 30 degrees, mg over 2 sine theta, mg over 2 sine 30. The sine of 30 is 1/2. 2 times 1/2 is 1. At 30 degrees, you have to pull along the orange tension direction with the same weight as the box in each cable. So you're pulling with 10 newtons in each cable to hold up 10 newtons because, again, you have foreshortened the vertical component and elongated the horizontal component. The blue component is what holds up the box. The horizontal component does not hold up the box. It would be trying to pull it to the side, and there would be another one over here in its mirror image, canceling it out. Let's take a look at 15 degrees. At 15 degrees, your angle is so shallow that your blue vertical component has nearly shrunken away. So to accommodate for this, to keep this blue value always equal to 5, you have to pull with a much stronger tension in the orange direction. 10 over 2 sine 15 gives you 19.3 newtons. So you're pulling with double the actual weight of the block in each cable just to hold it up when it's at a shallow angle of 15 degrees. And now let's take a look at the last example when the angle is 1 degree or less. When the angle is 1 degree or less, you have mg over 2 sine theta, 2 sine of 1. You have to pull in each cable with 286 newtons just to hold up a 10 newton box. Because the angle is so small, the blue vertical component has shrunken to near nothing, and you need to pull in the direction of the tension with such a large force that you can generate half the weight, which is 5 newtons for each side, just to hold up something that is only 10 newtons. And then I have a little chart here. What if I had half a degree, a quarter of a degree, a tenth of a degree? You can see that the amount of tension in the orange vector has to increase to 572, 1145, 2,864 newtons just to hold up a 10 newton box. And then, of course, what if the angle was 0? What if you tried to pull completely sideways to hold something up? Technically, you would need an infinite force. You can't produce that. The string would break. You cannot hold something up in the blue direction by pulling to the side in the green direction. And there it is, the explanation of tension in the hanging mass with two equal angles and a variation from 90 degrees all the way down to 0 degrees. I hope you enjoyed this video, and thank you for watching. I'll see you in the next video.